Okay, so in section 7.2, we're going to talk about two things, direction fields and Euler's method. And what you have here, and this example actually, you don't need to copy this example down, okay? This example is from section 7.2 in your textbook. If you look at the exercises, exercises 3, 4, 5, and 6, okay? So, right, Jinxon. So 3, 4, 5, if you go to your ebook, look at exercises 3, 4, 5, and 6. Okay, and what you have there in those exercises is you have 4 differential equations. Okay, and you are to match each differential equation with one of the direction fields below. Okay, now of course, what's a direction field? What's that mean? All right, so let's talk a little bit about this. Let's talk a little bit about this. So let me bring up the whiteboard here. Okay, and it might look familiar, Jinxon. It might. So the first differential equation A, says that y prime equals 2 minus y. Now, another way of saying this is, 2 minus y. Let me do it again. Hi, Elsie, I'm in class. Okay, so y prime equals 2 minus y. So that means dy dx. In this case, x is the independent variable and y is the dependent variable. Dy dx equals 2 minus y. Now what I'm going to do is I'm going to draw I'm going to try to draw, if I can, an x and a y-axis. Okay. Okay. Now we need to think about this differential equation. And what I'm going to do is I'm going to say, okay, if y equals 2, if y equals 2, then y prime would equal what? If y equal, I mean, here's our differential equation. It's an autonomous differential equation. And if we said, let's let y equals 2, then y prime is 0, because you have 2 minus 2, which is 0. So this means that, well, you know, what is this y equals 2? That's a horizontal line, right? That's a horizontal line, y equals 2. So if I were to draw a horizontal line here, okay, and let me just, there's 2 there. This is the line y equals 2. And what it's saying is that the derivative y prime equals 0. So whenever y equals 2, it doesn't matter what the x is. It doesn't matter what the x is. Hold on. anytime y equals 2, the derivative is 0. And so that means you have here, I'm going to try to draw a number of them if I can. It's just I don't know, this new, I'll just do it this way. Flat slopes, flat slopes. Okay, so along the line y equals 2, the slopes are going to I want to say this the right way. A derivative is a slope of a tangent line. So along the horizontal line y equals 2, any solution that satisfies this differential equation would have to have flat slopes. And in fact, y equals 2 is an equilibrium solution, right? Because y prime equals 0. So if we have an initial condition, where y equals 2, doesn't matter what the x is, if we have an initial condition like that, then the solution is going to be that horizontal line y equals 2. Now let's pick another value. Let's pick a value, and here's 0. Let's pick a value. I want to say this one moment here. One moment. Okay, let's pick some values over here. Okay, maybe, let me see here. I'll put 1 here, 0 here, -1, -2. And I'm going to put a point here, and a point here, and a point there. Now, let me just phrase it the way I want to phrase it here. Okay, so kind of separate things out a little bit here. If y were equal to -2, what's y prime going to be based on the differential equation? If y equals -2. 4, right? Because that's right, nothing else. Nathaniel, 2 minus -2 is 4. So this means then, when y equals 2, the tangent line has a steep slope of 4. This is slope equals 4. So slope equals 4. Here, slope equals 0. What about if y equals -1? If y equals -1, what's y prime equal to? 3. That's right, because 2 minus -1 equals 3. And so that means then, when y equals -1 here, slope will be a little, and this isn't perfectly drawn, but the slope will be a little shallower. Okay. What about here? What about here when y equals 1? What's the slope going to be? What's the slope going to be there based on this differential equation? When y equals 1, what's y prime? 1. That's right. So there, the slope gets even less steep. You see what I'm doing here? See what I'm doing? And we can also go up here. We can go to 3 and 4. So here's 3, here's 4. When y equals 3, what's y prime equal to? And please let me know if you have any questions. When y equals 3, when y equals 3, what's y prime equal to? It equals -1, because 2 minus 3 is -1, right? So that means then that over here, at y equals 3, sorry, hold on. One moment. Slope is -1. And then finally, at y equals 4, what's the slope? So when y equals 4, what's the slope? If we substitute in 4 here, what's y prime equal to? -2. That's right, Taj. And so that gets us a little bit steeper slope. Okay, so you see what we can do is we can, for every coordinate in the xy plane, the derivative has a value. And the value of the derivative stands, what is y prime? Y prime is dy dx. So any function y would have to obey the derivative instructions. So this is like a portion of the direction field. And if we go back to the now if we go back to this example for the first differential equation, what's the right choice going to be? 1, 2, 3, or 4? We haven't graphed the whole direction field, but we're just graphing a portion so we can tell which is the right choice. That's right. That's right. Because you see on number 3, okay, you have along the line y equals 2, it's flat there. That's an equilibrium solution. And the first graph also is flat at y equals 2. Okay. But hold on now, hold on. Want to be a little bit careful. So this would rule out 2, and it will rule out 4. So we have to choose now between 1 and 3. Well, notice that for number 3, for every y level, okay, the slopes are the same at every y level. Okay, maybe I'll put that in blue. If you pick a y level and look at the slopes that at the coordinates that have those y values, they're all the same. And if you look down here, pick a y value, and again the slopes are all the same for that y value. So, but in the first graph, that's not the case. In the first graph, it seems that the slopes of the tangent lines are not dependent on y alone, but also where x is. So it has to be choice 3. You see that? So what you have to do is these differential equations, you have to find good x and y values to help you. So now look at this second differential equation. Look at this second differential equation. Okay, let's look at the second one. Let me clear this is all in the recording, right? Let's look at this second differential equation. Y prime equals x times 2 minus y. What are for that differential equation, what are the equilibrium solutions? What are the equilibrium solutions? Right. X equals 0 and y equals 2. Okay, so that means then that if we look on the first graph, okay, if we look on the first graph here, and I always try to draw on the pictures in red, just sort of along the line, horizontal line, x equals 2, the tangent lines are flat. So slope of 0. So, y prime equals 0, y prime equals 0 for this b when x equals 0 and y equals 2. So when y equals 2, flat slopes. When x equals 0, which is the vertical line, the y-axis, do you also see flat slopes there? Are the slopes flat? Every point whose x-coordinate is 0, are the slopes flat? You see flat slopes there? Do they appear flat? They do. They do. So you see, you're not to pick the right graph. You're not like picking like 10 different points and figuring out a slope, and then and drawing a tangent line with that slope. You're judiciously picking your x and y values. So you're going to do the same thing for C and D, and you're going to see this problem in your assignment that's due next Thursday, where you're going to have to do graph direction fields and match direction. You're not going to have to graph the direction fields. You have to match the direction field with the particular differential equation. But that's how you do that. That's how you do that kind of problem. Okay. Graph 2 is also flat, Ange, but graph 2, no, actually, good question. If you look at, well, all right, graph 2, yes, graph 2 is flat along that vertical y-axis. But if you look at y equals 2 here, the graphs, the tangent lines are not flat like they are here. Probably what I should have done over here. I mean, it's okay. I'll just do it. These are my tangent lines, right? And they're all flat, but they're not flat here. So well, I want to be more careful. That isn't quite right, what I said. No, let me rephrase that. No, I didn't do that right. When y equals 2, there's a flat line, But you see, these lines here are not flat. Those are not flat, those lines. You know, whereas, yes, it's a little different. Whereas here, along the line y equals 2, all the tangent lines are flat, horizontal, have slope of 0. You see the difference? See the difference? Oh, I see what you mean. But okay, good. So that's what I mean. And what I said before just a moment ago wasn't right in terms of this graph here. These tangent lines here are for you know, y values of 2, and the slopes are not flat based on the direction field. Now let me show you something else. Here. Let me go to the ebook. One moment. Let me go to the ebook. Okay. I'm going to section 7.2. Okay. Just show you something here. One moment. Okay, so there in figure 1, well, I want to show this the right way. So in this problem, they have the differential equation y prime equals x plus y. And what they do is in figure 3, they have the direction field for the differential equation y prime equals x plus y. And what they did was they picked a lot of coordinates, okay, in the xy plane, and every coordinate they graphed, they computed a slope, which you can do because you have your differential equation. You can find the derivative, and so you can draw a tangent line with that slope. And the thing is, you can actually, once you know the direction field, you can actually graph a solution. You can graph a solution to, so like for instance, actually, let me go to, I want to go to figure 4 here. So in figure 4, you have the direction field for the differential equation y prime equals x plus y. And you see, they say, okay, I want to know the solution to the differential equation y prime equals x plus y. I want to know what that solution looks like if I require that solution to pass through the point 0, 1. Okay, so what they've drawn there, that purple solution in figure 4, is the solution to the differential equation y prime equals x plus y, and it passes through the solution passes through the coordinate 0, 1. So do you see how the solution obeys the direction field? Do you see that? How the solution obeys the direction field? The solution curve, the tangents to the solution curve at the different points match up. If you think about the slopes, if you think about this solution curve and you think about tangent lines to the solution curve, they agree with the direction field, right? You see that? How they agree? That means, and it has to, because the solution has to obey, the solution to the differential equation has to obey the differential equation. So the derivatives, the slopes at different points have to agree with the direction field. Let me see, maybe I can show you another example here. Look here, look at figure 6. Okay, this is here's another direction field. Okay, another direction field. Okay, and you see they draw a solution on the direction field. You see how the solution obeys the direction field? It's like think of current in a river. How many have been on a river or a small river or like a, I don't know, I'm not like a river that has maybe a few rapids or something. You're in a canoe or something like that, and you're going with the flow of the river. Okay, Taj Mahal and Ange, it's the same kind of thing here. You're going with the flow of the direction field. The solution has to obey the direction field. Here's an example here. Here's one, figure 8, where they've drawn on a direction field. Okay, the direction field, I should mention, these direction fields, I'll just mention it, they come from example 1 here, where they have a differential equation, y prime equals x squared plus y squared equals 1, and they've picked different coordinates and graphed and found slopes of tangent lines, and then they graph the direction field. Okay, that's what they've done. So okay, well, what if we wanted to draw some solution curves on the direction field for this example 1, and we're looking at figure 8. This is in section 7.2. You see there how all the solutions obey the direction field. They, depending where, I mean, different initial conditions give you different solutions. And the solutions follow the direction field. Is this making sense, class? Is this making sense? Please let me know if you're uncomfortable. Okay, Ange is okay. Ange is good. Okay, are there any questions on all you're doing in section? Okay, it's making some sense. Good, Taj, good. All you're doing in section 7.2 is like in the homework, in WebAssign, you're going to be given direction fields. Well, sometimes you'll be given differential equations and you have to match it with the right direction field. But you're never going to have to like draw a direction field out by plotting like, 20 points or something like that. Our goal here is for you to understand what direction fields mean. So 2 kinds of problems in the homework for 7.2. You'll be given direction fields, and you have to match. You'll be given a direction field, and you have to match the right. I'm sorry. You'll be given a differential equation, and you have to match the right direction field that goes with the differential equation. That's one kind of problem. The other kind of problem is you'll be given a direction field, and you'll be told, all right. Or you'll be given a differential equation. I'm going to say this the right way. You'll be given a differential equation with an initial value, and you have to find the right direction field that has the correct solution curve with it. So, like for instance, in this problem here, okay, if I were to say I want the solution that passes through the origin, okay, I want a solution that obeys the differential equation but passes through the origin. Which color would I be choosing? Yellow, black, purple, green, or that other color? Which is the right solution that passes through the origin? The purple one. That's right, Ange. Okay. What if I want a solution that passed through, let's say 0, -1? I want the solution to the differential equation that passes through the point 0, -1. Would it be the yellow, black, purple, green, or that other color? It'd be the green. Good. So that's right, D'Angelo. That's right, Angelo. So, and you have to be a little bit careful with these problems because they're multiple choice. You have limited number of tries, so you don't want to answer too quickly. Okay, you want to take your time. But are there any questions in general on this? Are there any questions in general on we'll be covering more of 7.2. We have to talk about Euler's method. We'll talk about that. We'll talk about that, well, next Thursday, right? But are there any questions on what you've learned here? Give me a thumbs up if you're feeling comfortable. I love it when I see like a Christmas tree of lights popping up there. Okay, Nathaniel, Jan, Ange, Taj, Javier. Good, good, excellent, excellent. David, D'Angelo, Joseph, wonderful. Okay, well then I'm gonna stop the recording. This is we're what we've covered for today. Okay, excellent. Let me stop the recording.